Hi, this is Mr. Barron. What I'm going to be showing you is the new unit that we're going to be learning, which is solutions. Once you go to the unit pages for chemistry, the first year chemistry, click on the unit Solutions. When you're on the Solutions unit, pay attention to the learning goals that are there. These links, more than any other unit, are going to be immensely helpful for you in the process of studying. What we're going to do is we're going to begin with a PowerPoint that's going to overview what solutions are and why we study them. So I'm going to go back to the beginning of my PowerPoint here and obviously pay attention to the nasty glass of water with the stuff in it. That's what we call a mixture. And part of solutions chemistry is being able to separate out mixtures. All right, so what we're going to do is we're going to move ahead to the next slide where we talk about matter. So matter, we of course know, is, we have solids, liquids, and gases. Well, matter can be thus divided into mixtures and pure substances. There are two types of mixtures, heterogeneous and homogeneous, and pure substances fall into elements or compounds. A homogeneous mixture is one which all of the solute, the thing getting dissolved or the thing being mixed together, is spread out evenly. Homo means same, so if I look in the top part, it looks the same as the bottom part. Hetero means different, so a heterogeneous mixture obviously looks different in different parts of the mixture. And pure substances have the same composition throughout. Why don't you pause the presentation and go ahead and read through and write down a sentence that defines and summarizes for you what heterogeneous versus homogeneous is. All right, now, pure substances. Pure substances break down into elements and compounds, of course, and with elements, they can be both atoms and molecules. Compounds can be molecules and ions. Make sure you pause the presentation and look at the examples of each of them. All right, now we're going to do a little quiz to see if you know the difference between examples of pure substances, mixtures, heterogeneous, and homogeneous. So when we look at these two, in your answer, you're going to come up with in your head A or B. Hopefully you put A, pure substance. Next one. Hopefully you put B, mixture. The answer for this one is A, it's a pure substance. Argon is an element. And, I already gave you the answer for the next part, is that argon is an element, not a compound. All right, pure substance or mixture. Hopefully in your head you're thinking mixture. Now what type of mixture? Not the same throughout the entire composition. It's not exactly the same spread out evenly, so this would be a heterogeneous mixture. Carbon dioxide, hopefully you put compound. The reason carbon dioxide is a compound and not an element is because there are two different elements present in it. The opposite of this would be an example of bromine. That's an element. Even though there are two bromines, they're both of the same element, so we consider it an element. All of the elements that are gases all the elements that we've talked about in the past, not all gases, but the diatomic elements of the periodic table, Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, all of those are considered elements. All right, moving on. So now let's talk about the dissolving process. So some things don't dissolve. An example of this is oil and water. We can see that they're separated. So I did a demo that showed you the difference between things that are miscible and things that are immiscible, and explain the key way that we can remember how things dissolve, and we said that like dissolves like. Once you pause the presentation, make sure you have this down in your notes. All right, so how does soap work? How does soap take oil and dirt off of our bodies when we use soap on our hands? All right, so how does this work? Well, we'll notice that this soap molecule right here has a part of it that looks a lot like water. Both of these parts are polar, so they can dissolve in water. This part is not similar to the water molecule. So this actually can get dissolved in the oil. So what happens is this part is miscible with the water, this part is miscible with the oil. So the soap can actually dissolve both. It's similar because the head of it has a polar end and the tail of it has a non-polar end. And here's an example of a number of soap molecules. All right, so let's talk about the dissolving process and also how things dissolve more specifically. Well, we have some vocabulary we need to know. We need to know the difference between solutes, solvents, and solutions. Solutes get dissolved. The solvent does the dissolving, and the solution is a very specific homogeneous mixture after the solute and the solvent have combined. Let's go to my animation where I am going to show you salt dissolving in water. I'm going to take my solute and shake it into my solvent. You can see that all of this salt is breaking apart into the ions. We have a name for that. We call that dissociation. You might want to spell that out. D-I-S-S-O-C-I-A-T-I-O-N, dissociation. So what we're going to do is we're going to zoom in and look more carefully at what's happening when these salt particles dissociate. I'm going to go to one of these links. I'm going to click on the dissolving process, not the one with the narration, although you should probably click on that later. And let's take a look at how the water molecules are literally pulling the salt apart. When you look at it carefully, you'll see that the water molecules have obviously their oxygen, which is symbolized by red, and two hydrogens, which are symbolized in white. Let's take a close-up view of how some of these ions are being pulled off the salt crystal. So when we look at these water molecules, it looks like they're almost attacking and pulling into solution this ion. This ion turns out to be negative. We know that it's a negative ion, we can tell because notice all the water molecules have the hydrogen ends pointing towards it. See, water is a polar molecule. That means that it has a charge. One end of it's partially negative and the other end of it's partially positive. Well, opposite charges attract, and the partial positive end of the water molecule is attracted to the negative charge of the ion. Let's go back and take a close-up view of another ion being pulled into solution. This time we see it's the partial negative part of water molecule that's pulling the ion into solution. We can see that the positive ion has been pulled into solution by the partial negative side of the water molecule. So it's important to know that that is what's happening when dissociation is occurring, when a salt is dissolving in water. So let me keep adding solute. If I keep adding solute, I'm going to get to a point where I don't have enough solvent to dissolve all of my salt. And you'll see salt still left over in the bottom. You've probably seen this with solutions you've made at your own at home. What you'll do is you'll make a drink and you'll see something, you can't totally mix that drink and you can't get all of the solute dissolved. Well, one way to get all the solute dissolved is to dilute it even further. If I increase the amount of solvent, then I can dissolve that salt that was not dissolved before. Now, how do I get these ions by themselves and separate it from the water? Well, most of you might be thinking, well, turn on this end. Well, that's not going to work because both the solute and the solvent are going to come out. And eventually this salt's going to be dissolved as well. So remember that there is something called concentration. Concentration is the ratio of solute per solvent. If I have too much solute, let me show the example of too much solute again, then not all of it will dissolve. We have a name for that when not all of it's dissolving. We call it a saturated solution. A unsaturated solution is where I have more than enough solvent to dissolve all of my solute. And a supersaturated solution is when I can dissolve more of it than at normal conditions, typically at a higher temperature. An example of that would be making something like simple syrup. All right, now there are salts that don't totally dissolve. They partially dissolve. We call them slightly soluble salts. You'll notice that even though it appears there's more than enough solvent to dissolve all of the salt, like in the last example, not all of it is dissolving. So there are some salts based on the charges and how the ions are packed that don't totally dissolve, and we call them slightly soluble. There are also salts that are totally insoluble, that don't dissolve at all. All right, let's go back to our presentation. So how do we separate things out? There are a couple of different processes that we can use to separate out mixtures. One of them is chromatography. Chromatography is a chemical process to separate out mixtures of molecules based on their solubility, how much they dissolve. Remember, how much they dissolve often has to do with what we call intermolecular forces. An intermolecular force is a force between molecules. An example of that would be right here, where we saw that there was a strong intermolecular force between the positive ions in the salt crystal and water, and that's why it was dissolving. All right, so continuing on, chromatography has, usually we use paper as a stationary phase, and then we have a solvent, and then we dot the paper, and when we dot the paper with the mixture, we let the solvent rise up, and the solvent dissolves the molecules that we put on it in different rates. So let's show what it looks like. So what I have here is I'm going to dot my piece of chromatography paper with 3 samples. One with a green dye, one with a yellow dye, one with a blue dye. And now what I'm going to do is put the solvent in the bottom of the paper and let that paper soak up all of the solvent, and you'll see the solvent rise. The solvent is what we call the mobile phase. That's what's going to do the dissolving in these mixtures that I've placed here. So it's going to rise, and you'll see the green gets separated into blue and yellow. So there was only blue and yellow dyes present in the green dye, or in the green mixture, so we know it was a mixture. We see that blue is at the top of our paper. The reason blue is at the top of our paper is that blue is more soluble in that mobile phase than the yellow, because the yellow doesn't dissolve as well in that liquid. It sticks to the stationary phase a little bit more and doesn't get carried up quite the same as the blue dye does. So another technique that we can use to separate things out is by forming a precipitate. We can actually mix two things that are aqueous and then form a precipitate, salt or something that is not soluble. We can also filter things out if the particle size is large enough. Filter paper will often do that. Then we can distill, and distillation is separating out compounds based on their boiling point. An example of this is we have the flask here with our mixture, and we slowly heat it, and at different temperatures, the molecules that we have in this flask will boil at different temperatures. Then once they boil, they're forced into this tube here, which we call the condenser, and the condenser cools down those gases so that they can go back into a liquid, and we can separate out that mixture at different temperatures, using different temperatures, and because the molecules boil off at different temperatures, we can separate them out. We can also use fractional freezing. We can separate out mixtures based on the freezing points of two liquids if one freezes before the other. Some compounds are actually magnetic, so we can actually pull them out using a magnet. And also, don't forget, there's always differences in solubility. Some compounds don't dissolve in water or oil or alcohol and fall to the bottom like a snow globe. All right, let's take a look at the mixtures we have here. So we can see here that we have in the top left an example of a homogeneous mixture. It's a solution. Solutions are always homogeneous because our solute is evenly spread out. It's the same, the top, the bottom, all over. We also have something called a colloid. What a colloid is if you have particles that cause light to be distorted. A suspension is when you have a clear separation between the two things that are being mixed. And then pure substances are where it's just a compound or an element. We've talked about that before. All right. So suspensions we consider are heterogeneous mixtures where the particles are large enough to not dissolve and eventually settle to the bottom of the fluid due to gravity. A colloid is a homogeneous mixture where particles are small enough to be dispersed evenly by random molecular motion, but are large enough to scatter light. A good example of this is the fat in milk, and that causes milk to be a colloid because it scatters the light, but it's distributed homogeneously, even though they don't necessarily dissolve. The Tyndall effect is one way to identify the difference between a solution and a colloid. So if light's passing through the room and you see white, that's because you see the light scattering. And actually, believe it or not, when you have a lot of dust in the room, you can consider it a colloid. That dust is being kept in the air by random molecular motion, and that dust is not dissolving in the air, so you get the scattering of the light when the light hits those particles. That can also happen in mixtures where we're dealing with liquids. So an example is on the left, not a colloid. On the example on the right, it is a colloid because light's shining through both of these. So we can see how light's scattered clearly in the colloid. An emulsion is a type of colloid that is specifically two or more are immiscible, unblendable. Think of immiscible as unblendable liquids that scatter light. We also have things called surfactants, and what they do is stabilize emulsions to prevent the liquids from separating out like oil and water. Detergent is an example of a surfactant. So back to what solutions are. Solutions are homogeneous mixtures. And if we're going to put these all on a scale in terms of particle size, or suspensions, the particles are large enough that they actually settle out. Colloids, they don't settle out, it's homogeneous. In solutions, the particle size is small enough, much smaller, that they don't scatter light. So we've looked at before the example of the dissolving process. Remember, dissolving is not melting. Phase changes are only caused by changes in heat and pressure. Dissolving is a totally different process. Don't forget that at the particle level of dissolving, the only reason salt dissolves in water, NaCl, is because there's a greater attraction between the Na plus and water than there is between the Na plus and the Cl minus. The solvent-solute attraction has to be greater than the solute-solute attraction. Don't forget the terms that we've had as far as solutes and solvents. All right, now, what are the things that cause things to dissolve faster? Surface area. The higher the surface area, the faster a solute will dissolve. You've probably done this when you've made solutions before. You've taken a cube of something, say like a cube of sugar, and you've chopped it up, or you've broken it apart. And when you break it apart, you create sides that wouldn't normally be exposed to your solvent. So if I chop this in half, I'm creating something that didn't exist before, and that's a new side. And that side is where the solvent can attack and dissolve whatever you're trying to dissolve. Also, temperature is a variable. The higher the temperature, the faster something will dissolve. Saturated solutions. are a solution where no more solute can dissolve. I've shown that before with my salt shaker. And a classic example of a supersaturated solution is where you can heat it up to the point where you are holding more solute in it than at normal conditions. And then you can do something that causes it to crash out, and then you'll see it precipitate out, or at least you'll see the solute come out. Solubility is how much a salt can dissolve before a solution becomes saturated. Temperature typically raises the solubility of the salt, but it decreases it for gases. See all of these salts? When we increase the temperature, we're able to get more and more salt dissolved in our water. There are examples where salts aren't like that, and the higher the temperature you get, you're not able to dissolve more. But that's the general trend, that the higher the temperature, the more of it dissolves. Also, gases, it's the exact opposite. Gases are more soluble at lower temperatures, not higher temperatures. This is why a soda often goes flat faster on a warm day than in a refrigerator. So, talking about sodas becoming flat. Henry's law: the higher the pressure, the more soluble a gas can become in a solution. So if we have carbon dioxide and we have a higher pressure of carbon dioxide, we're going to be able to dissolve more of that gas in the liquid. Again, the higher the temperature, the more of these the more of the gas molecules come out of solution. So a classic example of Henry's law is opening up a soda can. When you do that, you drop the pressure, and when the pressure drops, the carbon dioxide comes out of solution. So again, Henry's law is that relationship between pressure and how much gas dissolves in a solution. Vapor pressure can also be affected by adding a solute. So if I have just water, it will evaporate and exert force on this column of mercury. You'll look over here on the left that there's a solute that we dissolved, and we actually have a solution, a mixture here. That those solute particles are actually holding on to the water molecules and preventing them from completely evaporating away and pushing on the column of mercury. So if you increase the amount of solute in your mixture, the lower your vapor pressure, less of the water is going to be able to exert force on that column of mercury. Boiling point depression and raising the boiling point and freezing point depression can happen with a solute. So salts that dissolve in water will typically lower the freezing point and raise the boiling point. The boiling point gets raised because the salt's intermolecular attraction prevents it from escaping in the gas phase. Freezing point depression occurs because the salt disrupts the crystal lattice of water when it begins to freeze, keeping it a liquid. So this is a classic example of why some people add salt to water when they're boiling pasta. When you add salt to the water, since the salt has an intermolecular attraction with the water, prevents that water from boiling sooner. So what happens is that the boiling temperature is a lot higher. So once you do see the water starting to boil, it's not at as low of a temperature as it was before. It's actually at a higher temperature. So in theory, you could actually cook your pasta at a higher temperature, and in theory it would cook faster, because when you see the water boiling, it's not just boiling at 100 degrees Celsius when you have salt in that water. It's boiling at about 104 degrees Celsius. So, dissociation we've talked about before. Dissociation is the breaking apart of ionic compounds. That's a classic example of it. Whenever that happens, you form an electrolyte in the solution. And an electrolyte is a solution that can carry an electrical charge. Non-electrolyte solutions are those in which whatever you're dissolving in your water cannot carry a current. So electrolytes, we said, are free ions dissolved in solution that can carry an electrical current. The more electrolyte dissolves, basically breaks up, dissociates, the stronger of an electrolyte it is. So potassium chloride is a strong electrolyte. That means when I put KCl in water, 98% of it breaks apart. If I put vinegar or some other weak electrolyte in water, what will happen is that most of it sticks together and doesn't break apart. You need ions in solution in order to carry an electrical current. So a classic example of this is I have an electrolyte in this solution, and it's able to complete the circuit and light up the light bulb. I have a non-electrolyte in this mixture, and it's not, since there are no ions in solution, it's not able to carry an electrical current, and the light bulb circuit is not complete, so the light bulb does not light up. Here's some examples of strong and weak electrolytes and non-electrolytes. Now we're going to talk about one last type of mixture. You can also have gases dissolved in gases. Classic example of this would be ozone, which is actually the most common type of air pollution that you see in large cities like Los Angeles. Pollution we want to think of as a solute, and that's something that gets reported out in measurement readings. So we've gone over a lot of the basic vocabulary of solutions. What I want you to do after this presentation is I want you to go back to the solutions unit page, and I want you to click on all of these links and make sure you're clear on all of the vocabulary that's in this unit. The terminology is really important, otherwise we can't do a lot of the cool labs that we have in this chapter. Thank you.